Alright, so in this section, we'll learn the procedure to compile the Linux source code to generate the Linux kernel binary. Alright, so now before that, let's download the Linux kernel source and let's understand its source tree. Okay, so now to download the Linux source code for your board, okay, that is Beaglebone Black or Beagleboard. So you have to visit the official Beagleboard and Beaglebone kernel repository at this link. Okay, so I have already given this link in the resource section, so you can go ahead and download the latest kernel which is available, which is 4.4.68. okay, so all you have to do is just click here and you can either download it as a zip, okay, or you can use this link. You just click here to copy and then you can clone from this address. Okay, so to clone it, you have to go to your terminal and you have to type the command git clone. Okay, and then you have to mention the repository address from where you want to download, okay, or clone. So sometime what happens is the git command may not be there in your PC. So in that case, you have to first install the git command. For that just type apt-get install git. Okay, and here you can see that it is saying git is already the newest version. Okay, so now after that you have to type git clone and the address. All right, so what this command actually does is it will clone the Linux kernel from this repository into your PC under this directory called Linux. Okay, it will create a directory called Linux. Okay, so just go ahead and clone this directory, or you can also download it as a zip. Okay, so downloading it as a zip actually saves you lots of time, but cloning is actually slower comparing to downloading as a zip folder. Okay, great. So either way you can do that, and after completion of the cloning or download, you will have this directory, and just enter into that directory, and this is a kernel source code we just cloned into our PC. Okay, now in this lecture, let's first explore the directory structure of the Linux kernel source to understand how Linux runs on different processor architectures like x86, ARM, PowerPC, AVR, etc. You might have already seen this picture, which shows the relationship between the processor, SoC, and the board or a product, right? So now the source codes to handle all these three components, that is the processor, SoC, and the board, are systematically arranged in the Linux kernel source tree at different directories. So first, let's explore that. Now, since our architecture is based on ARM, all the codes related to handle those devices which are based on this ARM architecture is present in the directory called arch-arm. Okay, so suppose if you want to run Linux on ARM based devices, then this is the directory to look into to explore the processor specific, SoC specific, and board specific details. Okay, at the same time, all the codes related to handle those devices which are based on, let's say, PowerPC architecture will be present in the directory arch PowerPC. Okay, so Linux supports running on these various different processor architectures. Now let's explore the ARM code organization in the Linux kernel source tree. The core ARM processor related codes, like to handle the memory management unit of the processor, or to handle cache memories, exceptions of the processors, etc. will go into these directories. Okay, so you might have seen some of these when I was explaining the Linux kernel boot sequences. Now, the code specific to the SoC will go into this directory, which has a prefix Mac. Okay, for example, the AM335X or OMAP2 or 3 or 4 SoC specific codes from Texas Instruments will live in this directory, Arch, ARM, Mac, OMAP2. Okay, or you can call that as machine OMAP2. All right, the code related to Texas Instruments DaVinci family of SoCs will live in this directory. The SoC specific codes related to, let's say, Qualcomm's SoCs will go into this directory. So basically, every vendor of the SoC has their own machine directory to keep their SoC specific source codes which are needed to work with SoCs produced by the vendor. Okay, so now strictly speaking, this machine specific directory has two parts as shown in this figure. One is board related, okay, and another one is machine shared common code, or also you can say that SoC shared common code. Okay, the board file is a C source file which explains the various peripherals on your board outside the SoC. Okay, so this file usually contains the registration functions of various devices found outside the SoC, like your Ethernet PHY, WPROMs, LEDs, LCDs, etc. So basically, the vendor uses this file to register his various board peripherals with the Linux subsystem. And the machine shared common code contains various C source files which contain the helper functions to initialize and deal with the various on-chip peripherals of the SoC, and the codes are common among all the SoCs which share common IP for the peripherals. Okay, for example, the AM335X SoC is actually belongs to Sitara family of SoCs by Texas Instruments. Okay, but still there is no directory called machine Sitara in Linux, but there is a directory called machine DaVinci. So you can see here, that's because the DaVinci SoCs are for different market purpose. These SoCs are actually targeted for video applications. So the peripheral IPs are entirely different and they need different codes to handle them. But in the case of AM335X, even though the SoC belongs to different family than OMAP, most of the peripheral IPs are exactly same as OMAP2 or OMAP3-4 family of SoCs. Okay, so hence they still refer to machine OMAP2 directory for AM335X. Okay, so whereas machine OMAP1 contains all the SoC shared common code to handle peripherals of the SoCs which are based on OMAP1 family only. So what are the important files you find in the machine OMAP2 directory? So you will find the helper functions for the various peripherals, finmuxing, power management, clocking, etc. Okay, the SoC has different peripherals, right? Like SPI controller, I2C controller, high-speed MMC controller, clocking engine, GPIOs, serial ports, etc. So you will find various C source files here related to different peripherals which will help you to initialize those peripherals and provides lots of helper functions to deal with those peripherals, including pinmuxing related helper functions. And note that you can even change this file if required according to your product design. Okay, and you should also remember that these source files are actually common among all the SoCs which share the same IP as OMAP2 SoC. Okay. Alright, so now let's explore more about the board specific configuration files you find in this directory. Okay, so I will cover that in the next lecture.